and go deeper into the atom, to the atomic nucleus, where available energies dwarf those available to electrons. This is nuclear physics, a topic of great public interest and public fear, not unlike the fear of electricity when it was in its infancy. The story of radioactivity goes back to the discovery of X-rays. In 1895, the German physicist William Röntgen discovered rays of an unknown nature produced when a beam of electrons struck the glass surface of a glass discharge tube. These were called X-rays because they were unknown at the time. They could pass through solid materials, could ionize the air, and were undeflected by magnetic fields. Today we know that X-rays are high-frequency electromagnetic waves usually emitted by the de-excitation of the innermost orbital electrons of atoms. The X-ray photo shows that these rays penetrate flesh more readily than bone. A few months later, the French physicist Antoine-Henri Becquerel stumbled upon a new kind of penetrating radiation. One night, Becquerel left a wrapped photographic plate in a drawer next to some crystals that contained uranium. The next day, he discovered to his surprise that the photographic plate had been darkened, apparently by spontaneous radiation from the uranium. He proceeded to show that this new radiation was like X-rays in that it could ionize air, but was different in that it could be deflected by magnetic fields. Becquerel's radiation emanated from processes inside unstable atoms. Later, scientists found that this instability, or radioactivity, resides in the atomic nucleus. More than 99.9% of the atoms in our everyday environment are stable, but some kind of atoms are unstable. All elements having an atomic number greater than 82, lead, are radioactive. It was soon found that there are three distinct types of radiation, named for the first three letters of the Greek alphabet: alpha, beta, and gamma. Alpha rays have a positive electric charge, beta rays have a negative charge, and gamma rays have no charge at all. The three rays can be separated by placing a magnetic field across their paths. Further investigation showed the alpha ray to be a stream of helium nuclei, and a beta ray a stream of electrons. We commonly call these alpha particles and beta particles. As said in an earlier cast, a gamma ray is electromagnetic radiation, a stream of photons, whose frequency is even higher than that of X-rays. Notice that in a magnetic field, alpha rays bend one way, beta rays bend the other way. Alpha particles are positively charged and betas are negatively charged. Beta rays are streams of electrons ejected from the atomic nuclei, not electrons coming from orbits outside the nucleus. Note that gamma rays don't bend at all, having no electric charge. The combined beam comes from a radioactive source placed at the bottom of a hole drilled in a lead block. Alpha particles are the least penetrating and can be stopped by a few sheets of paper. Beta particles will readily pass through the paper, but not through a sheet of aluminum. Gamma rays penetrate several centimeters into solid lead. These radiations were also encountered by Marie and Pierre Curie while investigating the emission of radiation by thorium, actinium, and two new elements they discovered in the process, polonium and radium. Gamma rays, as it turned out, were the result not of changes in the electric energy states of the atom, but of changes occurring within the central atomic core, the nucleus. The term radioactivity was coined by Marie Curie. Because it involves the decay of the atomic nucleus, it is often called radioactive decay. Radiation is measured with various detectors, the most common being a Geiger counter, and a more sensitive scintillation counter. Inside the glass-filled tube of the Geiger counter, incoming radiation ionizes gas and triggers sharp pulses of current. The scintillation counter, more sensitive, registers incoming radiation by flashes of light produced when beta or gamma rays pass into a photosensitive crystal. Here's University of Melbourne professor Roger Rasool with the scintillation counter. Roger is showing that the paths of gamma rays are unaffected by a magnetic field. University of Oregon's Stan Miklavzina uses a Geiger counter to measure the radioactivity from a Fiestaware salt shaker. In the 1930s, Fiestaware used uranium ore in the ceramic glaze to obtain the reddish color. We all know that Earth's interior is a hot place. But why is it hot down there? It's hot due to the extensive radioactive processes in Earth's interior. The lava that is near Lil and me in this photo in Hawaii is hot, mostly due to radioactivity beneath. Radioactive decay in Earth's interior heats the water that feeds hot springs worldwide. These impressive ones, loaded with calcium carbonate, are in Pamukkale, Turkey. And young William Davis enjoys the heating effect on waters that spurt from Earth, geysers. Radioactivity is all around us and always has been. There are a lot of things in this world to be frightened about. In my view, radioactivity is not one of them. Its dangers are overblown, too much so. More on radioactivity in the next lesson. For now, I want to leave you with a question. Is radioactivity something new in Earth's history, or does it go back to its beginnings? Until next time, good energy.